Hey guys, welcome back. What we're going to be taking a look today is the magnets in the GAN 11M Pro on a virtual cube that I've looked at from the top of the cube. And what we're going to be doing is we're going to take a look at the traditional corner to edge magnet. The corner to edge magnet, that would be the top corner connected to the one below it, rotating on this green dot. That would be the path that that magnet would take to connect to the other edge magnet at the same spot. And we're also going to be taking a look at the magnets from the new corner to core from that one position all the way to the other position. And the magic number here is 16. And this is probably going to give you some indication on why the GAN 11M Pro has a different feel as far as magnets go. Now, if you're curious about all the math, I'm going to do a different video for the math, assuming it's requested. But here are the equations I used for the cube, just standard straight up and down lines, and I use some dotted lines for the actual position. I guess this one should also be dotted, shouldn't it? Let's fix that now. I don't like that. We'll fix that guy to a dotted line. Um, This is the equation I did for the edge positions. Notice I took the very center of that corner piece because the center of that corner piece on the very bottom would connect to the edge piece there. I called that point 2,2. Then I made a circle equation in blue right there to let it revolve around. I did it as a polar coordinate as well, so then I could have a moving point fixed with a angle measurement between 45 degrees or pi over 4 and 135 degrees or 3 pi over 4, and that allows this point to travel. And I'm going to use a little bit of math to explain, using this distance between that green point and the black points, how strong the magnet is. Now, is this an exact science? It's not perfect because I have not ripped my GAN 11M Pro apart and measured it to the nearest millimeter, but this should give you a close indication on how and why this cube feels as different as it does. Number one, the cube's very, very light. So what do you need to counteract a very, very light cube? You need different types of magnets, or the cube's going to seem uncontrollable. So that's what we're going to talk about today. So there's the edge positions, not too interesting. Here's the corner positions. Once again, not too interesting. I just put the corner magnet right there at the edge of the corner, even though I know it goes a little bit further in, making our results even better. We'll talk about that later. Did the same thing, got some points. I got a circle. I wrote the equation of a circle in polar coordinate form as far as a parametric equation goes. And I couldn't call it R theta again like I did up here because Desmos only allows you to use an R theta once. I couldn't do an R sub 1 theta and an R sub 2 theta. Nevertheless, let's get into the more interesting part of this. This number 16 is going to be prevalent, and we will tell why 16 is so prevalent. It is even the name of the video, Strength 16. Oh my goodness. So let's take a look at this stuff. What I've done here is this equation has a bouncing between pi over 4 and 3 pi over 4, or a 45-degree angle right here, all the way to a 335-degree angle over here. This would be the corner to edge magnet on the bottom part of the top of the cube, going to the other corner to edge magnet over here. Notice I have that 0.22, and then I'm subtracting the points down here. We're generically using the equation 1 over r squared, and this is used to calculate a lot of things in physics. For example, the attraction between two objects, and it conveniently also works for magnets. I'm not concerned about what the top value is because the top value would stay the same based on what type of magnet you're using. Let's just assume the magnets are the same, and we're going to use these numbers that we get to make some type of ratio to determine the strength difference between the magnets. This other one down here, this equation, that will represent the strength of the magnet that in motion here to the magnet on the left-hand side. And this value right here represents the midway point. Now, the midway point is the most important point we can talk about because that is the distance where this magnet strength right here from to this magnet and this magnet are equal. When this magnet, I'll pause it for a second. When this magnet is over here, even though this magnet over here doesn't seem like it is affecting it, it technically is, and this magnet's also affecting it too. Magnets, as long as their fields overlap, there's some type of attraction between those magnets. But I put this point right here because this is the point where the attraction between the two magnets is identical. I like to call that like my teeter-totter point, where the attraction between the left hand and right hand side are equal. And since we have some momentum or velocity towards the one side, obviously it will take over and start being more attracted to the other magnet. But you're going to take note that just to show you that the attraction was the same, I plugged in the point pi/2 or 90-degree angle right here to show you that the attraction between the two magnets is identical. That's my edge attraction. Now, the corner attraction, I did the same exact thing. And if we take a look at this, it's pretty straightforward. I did the same thing. I do the corner magnet attraction. We'll play A. Once again, the first one represents the attraction between the point and the right hand side. The second one represents between the point and the left hand side. And once again, the midway point or the teeter-totter point is that 90-degree angle. And notice at that 90-degree angle we have some coefficient value of 0.72. On the edge one, we only had an attraction value of 0.45. And if you take those numbers and divide them in some specific ratio, you get 16. This means that those magnets, core to edge, I don't care what type of magnet you're using, they're 16 times more effective. They're 16 times stronger in every single angle position compared to the same angle position for the other ones. That's how strong they are. You might say, well, what about in between plastic? You put plastic between two magnets. Well, guess what? If you look at this GAN 11M Pro, on the inside, it's literally magnet to magnet. So it's going to be even stronger than 16 times because the corner to edge magnets, guess what? They got plastic between them. The corner to core magnets do not have that. It looks like it's raw magnet to raw magnet, making it even stronger. And on top of that, I'm not even giving you exact measurements here. So the GAN 11M Pro, the core magnet system, is 16 times stronger in every single position even. Because you'll notice I've had this A value playing the whole time. And if I take this equation right here on the top and divide it by the bottom equation, this would be the corner to core magnet strength divided by the edge to corner magnet strength. It doesn't matter what A value it's at. If you compare them, it is always 16 times stronger. And this is assuming that you have fair magnets and there's no plastic between them. So that number 16 should be even higher because the corner to edge magnets, once again, have plastic between them, whereas the corner to core magnets do not. And you might be saying to yourself, man, that's quite the difference. If the magnets are so strong, why would they even need these edge magnets, the corner magnets? Well, think about this. When you do an M slice, what's not moving? When you do an M slice, you got it. The corners are not moving. So you need to have those edge magnets in place. Otherwise, your M slices won't really act as if they had magnets on them at all. It helps stabilize it. But the Valk Elite tried to do something interesting. They tried to do center cap to edge magnets, and it gave really strange feels on their M slices. That's because there was too much magnetic interference. If you're more interested in these magnet videos, like I said, I could talk to you all day about magnets in some of my other videos. I just figured I would do an opener. And hey, if you're interested in why these equations work and you're like, well, maybe he just waved his magic hands around and he said all of his equations were true, I'll make a video and explain to you why it's true. I hope you guys liked the video. Like and subscribe if you want to see more content like this. Adios.